Okay, we're rolling. This session is being recorded and will be posted later onto the recorded presentations page on my TCC Blackboard. On the schedule today, we have covering chapters 7 through 8 on IP addressing and subnetting. On Wednesday, we'll have a live lab session in SBS 1125 where we'll do this lab 6.4.3.5. Okay, hang loose one here, and I'm going to start the slideshow. Okay, first slide is up, Chapter 7, IP addressing. We're going to look at the legacy IP version 4 network addresses. These are the ones with the 32-bit addresses. Starting with a demonstration of converting between the binary number system and the decimal number system. We'll look at IP4 version addresses and look at what's the network portion of the address, what's the host portion of the address, and the dreaded, feared, and hated subnet mask. I don't like that term. It sounds like the Phantom of the Opera wearing a mask trying to hide something from you. I prefer to call it the network yardstick or the network ruler because it tells us how big the network is. Then we'll look at Unicast, broadcast, and multicast, which we had in the last, when we looked at data link layer stuff and Ethernet, they also had Unicast, broadcast, and multicast. We'll look at public and private addresses and certain reserved IP addresses. And there's someone join here. I have to click them in. And then we'll look at IP version 6, which was the solution that they came up with about 20 years ago, because 32-bit binary addresses, you only have a certain, about 4 billion numbers. That's not quite enough because the internet was just too popular. So IP version 6 addresses, they added more binary bits, and that should take care of the problem we had with the start in the mid-90s. We're just running out of IP addresses. So we'll look and compare IP version 6 to IP version 4. And then in the last section, we're going to look at our ping utility and the traceroute utility to see how we can check network connectivity. That's one very handy tool that we can use to see if we have IP connectivity within the network. The guys that came up with IP version 4 were very clever because they realized that if look at these 32-bit IP addresses down here, I'm just getting a headache just looking at all those strings of ones and zeros, and I'm supposed to look at 2 of them and compare them with each other and figure out if they're the same or they're different. So instead, they came up with this scheme of dividing the 32-bit binary code into 4 8-bit groups and make one of those 8-bit groups, make it a decimal number because our eyes are more used to decimal values. So we're going to divide it into 4 decimal numbers, the 192.168 stuff. So IP addresses are expressed in this dotted decimal notation. It's much easier on the eyes. We can look at this graphic and very easily see that the PC1 is 10.10, PC2 is 11.10, and it's not so hard on the eyes as looking at strings of binary numbers. It's just too difficult to look at. So let's look at this process of converting between binary and decimal. So in the decimal number system, it's a base 10 system. The digits are powers of 10. In the binary number system, it's based upon powers of 2. So the first digit is based, let me put on my crayon here. So this is the ones position. 0 through 9 represent the 10 possible values you can have in the ones position. Here's the tens position, so whatever number is present in that position, we multiply by 10. Whatever number is in the 100s position, we multiply by 100. Whatever number is in the thousands position, we multiply by 1,000. So this number 3,210, we know here since second or third grade that these numbers have different values based upon what position they are in the total number. So in the binary number system, it's the same sort of a thing, except they're not powers of 10, like 10, 100, 1,000, and so forth. It's powers of 2 instead. So in the binary number system, we have powers of 2 instead of 1, 10, 100, 1,000, 10,000. We have numbers based upon powers of 2. The binary number system is used because computers are binary creatures and they're on or off. So instead of having 10 possible states, they only have 2 possible states. We can still represent any number in the decimal number system with binary numbers. We just use enough binary powers to represent it. So in the binary number system, in the first position, it's times 1, just like it is in the decimal number system. But instead of being in the second position, being up the times 10, it's times 2. So our powers are 1, 2, 4, 8, 16, 32, 64, and 128. We're going to express our IP version 4 numbers using this dotted decimal system. So there's 8 bits in each particular number. So we just have to use the first 8 powers here. So if the binary number is, for example, the binary number is 111000000, and we look at our placeholder values or positional values, that means 128 is set, it's on, 64 is on, and all the other values are 0. So when we add those up, the decimal equivalent of this number is 128 plus 64, so 192. So we want to convert a binary number to a decimal number. We're just going to take all those placeholder values that are 0, we're not going to add them up. But when they're set to 1, we're going to add up those numbers. So in this case, the number 11 and 6 zeros, that's the first number of our, we have a lot of IP addresses that seem to be 192.168.1.1. So this first number represents that first dotted decimal number, 192 in binary. To convert from decimal to binary, what we're going to do is take the decimal number and then look at it and see, is the decimal number 128 or bigger? If so, we're going to set that binary value to 1. And then we're going to subtract 128 from that number and repeat the process. If we look at the difference, and the next number is 64 or bigger, we're going to set the 1. If it's smaller, we're going to set it to 0. And we're going to convert this process until we come up with a binary number. So as an example, the number 198, we have our 192.168.10.11. So the number 198, we take the 198, and 198 is bigger than 128, so we subtract 128 away from that value, and we have 64. So we put a 1 in the first position, and then we have 64. We're going to subtract 64 from that. That'll give us 0. We'll set a 1, and all the remaining values is 0. How about 168? Okay, let's take that number. 192, is that equal to or bigger than 128? It is, so we'll set a 1. And we subtract that, when we subtract that 168 from 192, it's less than 64. So we put a 0 there. And then we take the next number, it's actually 40. We take the next number, is 40 bigger than 32? Yes, it is. We set the 1, subtract 32 from 40, we get an 8. And then 16 is too big, we skip it, we go to the 8. And that's how we come up with the bit value for that as well. Hang on for a second while I update my attendance. One, two, three, okay. We're up to date now. Now the third digit, the 10, down here in the lower left-hand corner. So let's take the binary value 10, the decimal value of 10, and convert it to the binary value. So 10 is smaller than 128, smaller than 64, smaller than 32, smaller than 16, but when we get to 8, 10 is bigger than 8. So we're going to set the 1 value, and that subtract 8 from 10, that leaves 2. Well, 2 is smaller than 4, so that's a 0. 2 is equal to 2, so we put a 1 there. So in binary, the value of 10 is 1010. That's kind of strange. 10 in decimal is 1010 in binary. Just something to hang your hat on. And how about the number 11 now? The number 11 is one bigger than this. So when we take 11, smaller, 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 smaller. Oh, it's bigger than 8. So we set the 1 position, set the 8-bit, subtract 8 from 11, we get 3. 3 is smaller than 4. Well, 3 is bigger than 2, so we set the 2-bit on. We have 1 left over, and that gives us the binary value for 11. Oh, nothing confusing about that, right? Now, let's look at the network and host portions of IP addresses. This is a hierarchical scheme that's very similar to telephone numbers with area codes, or the 9-digit zip code scheme. So in the telephone number system, the 817 prefix is for the Fort Worth area. The 214 prefix is for the Dallas area. Then within the Fort Worth area, you have 7 digits that define the individual phone number at Fort Worth. So in IP addressing, the some part of the beginning numbers will be the network portion. Now, unlike the telephone number system, in America, the first 3 digits is always the area code. Well, there's some other countries that don't have as many people as America does, so they have different schemes for area codes. They might have 1 digit or 2 digits. In networking, we had the people that came up with the scheme in the early 80s were very clever in that they said some networks will be large, some networks will be medium, some networks will be small. So we're not going to make this a fixed number of network bits and a fixed number of host bits, which every network system previous to that had used. So they said, we'll come up with a scheme where we can have, well, 192.168.10.10, this is a fairly smallish network. We're going to talk about the number of host bits in a second. Whenever devices are on one network, like in a particular company or a floor of a building or something like that, they should have the same network prefix and the same scheme that if you want to call someone in Fort Worth from another Fort Worth number and you don't have to pay long distance calls, they're going to be in the same area code. Now, they destroyed that back in the 90s when everyone started getting pagers and fax machines and cell phones, and they had to come up with a number of additional area codes. It used to be that Fort Worth was all 817, Dallas was all 214. But the scheme here, the idea here is that when you're on the same network, you'll have the same network prefix. To tell us how many of these binary bits are the network part and how many bits are the host part, we use the subnet mask. I don't like the term subnet mask. I think it's the network ruler or the network yardstick. It's going to tell us, for example, the subnet mask 255.255.255.0 tells us the first 24 bits of the network portion, and the remaining 8 bits, the zeros, represents the host portion of that address. So when you configure, this is the network configuration screen for a Windows PC. Most other desktop operating systems like Mac OS X, Linux have a similar screens to configure them. And there's always these 4 important values that we configure: the IP address, the subnet mask, the default gateway, and a DNS value, because people don't want to type in numeric values. They want the DNS server to look up netacad.com or microsoft.com. So the 3 ones we have to have, in the Cisco labs, we don't have a DNS server, so we don't need to fill that out. There has to be a unique IP version for address, just like every cell phone has to have a unique 10-digit number, not allowed to share with somebody else. The subnet mask identifies which portion of this address is the network portion, the first part, and which portion of the address is the host portion. The default gateway in any network where we have more than one network and we're using routers to connect them together with, the default gateway is what I call the friendly neighborhood router. That's the address at which each host workstation can send the packet to. If it's not another device on that same network, you can directly communicate with them. They're all plugged into the same switch. But if he's plugged into some other switch, his intended destination is some other switch in another location or building or halfway across the world, he wouldn't have any means of directly connecting with them. He would have to send it to his default gateway, his router, and his router would look in his routing table and forward that message for him. So these are the 3 values we have to have. Now, if you only have one network and no other networks, like in some of the labs we did with the switches, you didn't have to fill in the default gateway value. But typically we're connected to other networks and we want connectivity with them. So the IP part, the IP address itself, 192.168.10.10 is our entire address. The network portion is the first 3 octets, 192.168.1. In the subnet mask, 255 in decimal is all ones. In binary, because 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 are 8 placeholder values, add up to 255. That's the biggest number we can have with an 8-bit value. If it's more than 255, it ain't an 8-bit value, it's more bits. So in networking, we're stuck with 8-bit values. So where we have the 255s in the subnet mask tells us this is the network portion of this IP address. And where we have zeros tells us this is the host portion of the IP address. Think of it like an area code and a local 7-digit number in the telephone system. Or in the zip code system, we've got the 5-digit zip code for your post office, and then the last 4 digits is the individual house or apartment. So logical ANDing sounds so confusing, but if we look at this chart down here, it's really 3rd grade multiplication. So let's look at this chart here. What's 1 times 1? It's 1. What's 0 times 1 is 0. 0 times 0 is 0, and 1 times 0 is 0. So the logical AND function is just simply multiplying the ones and zeros together. So no more than 3rd grade arithmetic required in introductory networking courses. You have to be able to determine that 1 times 1 is 1, and anything times 0 is 0. So anywhere that's 1, that means that's the network portion of the address, and anywhere it's 0, it means that's the host portion of the address. So what the subnet mask allows us to do is take this whole 32-bit IP address and determine what network is he a member of, and the ones strip off the network prefix and say the network portion is 192.168.10 and set the remaining host bits to 0. We're going to talk about in a second that the special reserved address in every bank of IP addresses, the definition of a network address is the host bits are 0. We'll talk about broadcast and stuff too, coming up real soon. If we look at the number of binary ones in a subnet mask, that is a shorthand, is instead of writing out all those 255.255.255s, for example, the most common network prefix in the world is 255.255.255.0. And if we count these ones here, there's 24 of them. That's where the /24 comes from. So you will oftentimes see networks with that shortcut version, the prefix length with /24. We put that / and just the number of network bits, the number of binary ones that was in the subnet mask. So let's look at these different types of addresses we have. The definition of a network address is the host portion is all 0. So we have here an example of 192.168.10.0/24. The /24 tells us that's the same thing as a subnet mask of 255.255.255.0. So the last octet of this dotted decimal address is 0. Binary decimal 0 is equal to 8 binary zeros. So anytime you see it in the host portion of the address, if it's all zeros, that's a special reserved address to denote the network itself. We're not allowed to assign that to host machines. The other one we're not allowed to assign to host machines is a broadcast address. So when we look at the host portion of a network address, of an IP address, if it's all ones, 255 is 8 ones, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. That's a special reserved address for the broadcast function. Now, what do we need broadcast for? They're evil. We should stamp them out. Well, we do need them for the ARP function. So if I'm going to ARP another neighbor to learn where his IP address is, what his MAC address is, I need to send it out to a broadcast address. The other big common use for the broadcast function is the DHCP function. When your workstation boots up, he sends out a broadcast request to assign him the right IP address to use in that company network or that home network. All the values in between are cool for us to assign to all of our individual workstations. So I've got 256 54 possible values that I could legally use to assign to a host workstation, from .1, .2, .3, all the way to 254. So in every range of IP addresses, we always lose 2 addresses. The all zeros value is reserved for the network identity, and the all ones value is reserved for the broadcast function. Now, everything in the lab we've done so far, we have statically assigned addresses. We have not clicked this button here that says obtain the IP address automatically. In the real world, you will definitely do that. That's the default, because you want some DHCP network server to assign IP addresses to everything. That's what you do at home with your home router. That's what companies and organizations always do. They have a DHCP server to assign IP addresses, because guys, it's just a total drag to have to go out and assign static IP addresses to workstations. And then they move to some other floor of a building and they have to change their addresses. And you got to go out and change them and keep track of the addresses that are used and which ones are available now. And I used to do this. And 1995 was about the time that the DHCP automatic address assignment function came into play. And I had about 250 people they were moving their things around all the time, moving their Macintosh workstations around all the time. And I would have to constantly assign a new static IP address to them. So in a small network, we can use static addresses. In our Network and Academy labs, these are small networks. We're going to do static addresses. Now, in a later course, we will cover the DHCP function. You'll set up a DHCP server, and you'll use it to assign IP addresses to workstations. Most devices will automatically get a DHCP dynamic address, workstations, employee workstations, home workstations. Some devices typically need a fixed address, a static address. Servers, printers, network devices like routers and switches, we give them fixed static addresses. But most devices are going to use DHCP. We're going to click that box that says obtain the IP address automatically. By default, when you install Windows or any other operating system, they automatically have that checked for you. And that way the DHCP server will give him his address and information, his IP address and default gateway and subnet mask and DNS server. Now, this looks kind of similar to what we talked about in the Ethernet chapter. Unicast is one-to-one communication from one machine to another machine. In this case, this host machine is sending something to be printed to the printer. He's sending a packet of pages to the printer. One-to-one, Unicast one-to-one communication. A broadcast is one-to-all. So I'm going to send it. Now remember what switches do when the switch encounters a broadcast? He floods it out to all the other ports. Because if I'm sending, for example, an ARP request to my router because I need to determine what his MAC address is, I need to send something to another network, I need to broadcast it to everybody so that I'll be sure that he hears it. So broadcast is sent to all other workstations. It's flooded out the switch ports to all other workstations. Multicasting is a sort of a kinder, gentler, almost like broadcasting, but people that aren't listening to that multicast group can sort of tune it out in the same sense that you can tune your FM radio station to one frequency and listen to that station, and somebody else can tune their FM radio station to another frequency and listen to that station, and you don't have to hear the station you don't want to. Because broadcasts are kind of evil. They sort of slow down all the other workstations on the network because every workstation has to process it before it decides it's not for him. So here's Unicast transmission, one-to-one communication. This workstation is printing to the printer. Broadcast transmission. How do we tell if it's a broadcast? Well, the host portion of the IP address will have all ones. This might be an ARP request or a DHCP request. Multicast transmission. This is typically used by routing protocols when they send routing table updates to their routing neighbors. Workstations aren't interested in this. They're not routers. They ignore them. Another thing that multicasting is commonly used for is when you tune into one of these internet-based FM type radio stations, music services, they don't send out, if they have 10,000 listeners, they don't send out 10,000 Unicast copies. That would consume too much bandwidth. They send out one copy and everybody listens to it, like you listen with an FM radio. You tune into that station. There are some addresses that are reserved for inside use. Example, at home, use the 192.168.1.network. It's typically used for home routers. That's a fairly small network because it only has a little over 200 addresses. Most home users, most small businesses, that's enough. The 172.16 block of addresses, that has like 65,000 addresses that are available. We use that for our Wi-Fi system that we have on the TCC campuses. The 10.0 block, well, gosh, that's millions of possible addresses. So many companies use that for their internal networks. We use it at the college for all of our desktop machines that are plugged into a wired Ethernet type connection. Now you're probably asking, if everybody uses that same number 10, isn't that a duplicate IP address? Isn't that a violation of the rules? Well, no, we're going to use a network address translation and convert that to some other address. So even though your home machine is 192.168.1.100 and my home machine is 192.168.1.100, they work together properly because I will be NATed to my AT&T address I get from the phone company, which is unique, a globally unique IP address. And you'll be NATed to your address that you get from Comcast or whatever cable company you hook to, and you'll have a unique IP address as well. And we'll study this NAT function in a later course. Okay, another special address is the 127.0.0.1. That's a special address for testing what we call the loopback. We want to make sure that our workstation has got the TCP/IP configuration check box has been checked. So we can ping 127.0.0.1. Even if we're not really plugged into a network, it'll work. It'll just prove that our Windows configuration is okay. This DHCP function that automatically assigns an IP address, what happens if the DHCP server goes bad or we've lost the connection to it? So as a workaround, Microsoft has generously donated the 169.254 prefix to this function of automatic private IP addressing, and a Windows workstation will just make up its own address. So if we have like the auditors are in the conference room with their 5 laptops and they're plugged together, but they're not plugged to the real network, they'll still be able to send their Excel files back and forth to each other with that. And workstations will listen. If they don't find the DHCP server, they'll keep listening, and when it comes back online, when the phone line comes back up, they'll automatically go back to their proper address that have connectivity with the rest of the world. The testnet addresses, 192.0.2, these are used in documentation and teaching purposes. So in the legacy world, we had classful addresses. Class A addresses began with their technical range is 0 to 127, but no network can begin with 0. That's the wild card. So it starts with 1, really. The Pentagon stole some of those values. We don't get all of them. 127 is reserved for the loopback address. There's a little over 100 Class A networks, and these were grabbed up very early by the big companies like Apple and Microsoft, Digital Equipment. All these people got all these Class A addresses, Cisco, for example. Class B addresses were from moderately sized companies. They have a network prefix that's 16 bits. So that gives us a company that needs about 65,000 host addresses. That would be proper for them. So in the 90s, when I worked for Harcourt, we had 167.208. I can't forget that because I had to statically configure it 10,000 times or so. So we only had about 12,000 employees, but we had 65,000 network addresses. It's kind of wasteful. Class C addresses, there's only 8 host bits. So 250 odd addresses that are available. That's good for residential or small business use. So this was a wasteful thing, and about the mid-1990s, we started having problems with running out of addresses. We were depleting all our available addresses. About the same time, the same thing happened, you remember, with the telephone system. All the fax machines and cell phones and pagers, we ran out of 817 numbers. So in Fort Worth, we had to add a bunch of different area codes and everywhere else in the country. So some band-aids that they came up with in the mid-1990s for networking was classless addressing. We weren't stuck with the small, medium, large, A, B, and C. We could make them custom sizes, so we didn't waste so many addresses. Assignment of IP addresses is done regionally. In the same sense that all the telephone companies in the world got together so they could place long distance calls and send the billing codes to the proper telephone company to pay. All the people that ran the internet in the various parts of the world got together and assigned. America has their American registry for internet numbers. All the different parts of the world have their registries for them. And they were allocated different ranges of class A, B, and C addresses until we started running out and had to do other stuff. Okay, now let's look at IP version 6. We were running out of these IP version 4 addresses. And we did some Band-Aid stuff. We did classless inter-domain routing. We did network address translation to try to keep it going. And then on a going forward basis, as the guy says in Dilbert, thank you for rolling out time travel. We're going to go on a going forward basis. We're going to switch from a 32-bit address to a 128-bit address. And that way we can have many more possible combinations than just the 4 billion or so we get with old legacy IP version 4. And we won't have to use network address translation. And now with the Internet of Things, we're going to have every parking meter and refrigerator and toaster is going to have IP addresses, so we'll have enough for everybody to use. The techniques for doing this are, let's run IP version 4 and IP version 6 simultaneously. We can keep using our old legacy IP version 4 and then gradually switch over to IP version 6 and stop using IP version 4. In the tunneling scheme, maybe our ISP that we use doesn't support IP version 6. We can tunnel the IP version 6 packet in, encapsulate it in an IP version 4 packet and send it through and then open it up again at the other end. And there was a translation scheme as well, and both these schemes have been deprecated. They're not recommended to being used now. We should go to IP version 6. So IP version 6 addresses, instead of being 32 bits in length, are 128 bits in length. And so instead of using dotted decimal, we're going to use something called hexadecimal, which is a base 16 system. This is why you see when we looked at that, this is the same scheme we used to do MAC addresses. Type ipconfig/all, and you'll see the hexadecimal value of the MAC address of your Ethernet adapter in your computer, and you're going to see some A, B, C, D, E's, and F's. So this is because in the base 16 system, we need a single character to represent what in decimal would be 10, 11, 12, 13, 14, and 15. We can't write 10, 11, 12, 13, 14, and 15 in decimal because that's a different number in hex. So A, B, C, D, E, and F are used instead. So in the IP version 6, we always write the numbers with 4 hex digits and a colon. And then we have a set of 8 of those. Now, sometimes we have a big string of zeros. So there are some rules that we can use here to reduce the number of digits we have to write down or type in when we configure this type of stuff. So the first rule is if there's any leading zeros, we can omit those zeros. So instead of having to type all these values out, we can simply omit the leading zeros. So this number is easier to type if you don't have to type all those extra zeros. So that's rule number 1, omit leading zeros. We do this with decimal anyway. If you write the number 111, you don't write 000 111, you just write the 111. You omit the leading zeros, it's natural. Okay, here's the second rule. If I have a bunch of zeros, I can collapse them to a double colon. So in this case of this number, first of all, we got rid of the leading zeros. But now we have some 2 octets, or hextets, I'm going to call them instead of octets, that are all zeros. We're allowed to do once and only once. We can replace a bunch of zeros that are all zeros next to each other with a double colon. So the zeros here were replaced with a double colon. Only can do it once. I can't do it twice. It would be too ambiguous. So we can do this once only. And then we can shorten that number. Now, do you remember Unicast and Multicast and Broadcast? Okay, so in IP version 6, we have the same thing. Except, well, we have Unicast 1-to-1. We have Multicast like routing tables or streaming FM radio station. But instead of calling it Broadcast, they call it Unicast. And they came up, the marketing guys, okay, it's time for Mark to rant. it's still the exact same function as a broadcast. Oh, I need to learn my neighbor's MAC address. I'll do an ARP request. I need to do a DHCP broadcast to learn my workstation address. So the marketing guys said, oh, we're going to get rid of all the broadcast. And what they really did is said, we're going to call it Unicast. It's another way of sending to all the other devices when you need to learn your neighbor's MAC address. Now subnet, oh, we haven't got subnetting yet. That's in the next slideshow. But subnetting can be the number of bits that can be the network prefix and the number of bits that can be the host bits. In IP version 4, I kind of have class A, B, and C addresses, so I can do variable length subnet masking and have all sorts of different values. In IP version 6 is actually easier because almost in every case, the first 128 bits, the first half of them, the 64 bits, is going to be the network prefix, the network identity. And the last 64 bits is going to be the host value, the interface ID. See the slash number here? So in IP version 4, we had /8, /16, /30, /24. In IP version 6, it's almost always /64. There's some different types of IP addresses. Global unicast addresses are like the IP version 4 global unique IP addresses, internet routable. Link local addresses, they're like the 10.172.16, 192.168 local addresses on the same link, and unique local is within a company to use to, so he doesn't have to consume addresses in the outside world. In the Cisco curriculum, we're typically going to use globally unique IP addresses, and then we'll use the what's called the link local address within our network to use an easy to type name for a router. The router, for example, is typically FE80::1. So they're in the FE8080 range, FE80::1 range. So he says here, typically the link local address is the default gateway for all the devices on the link. So here's our router, he's FE80::1. That's the default gateway value for all these other machines that are in that particular floor of the building or that particular company. Makes it easy to type. Now this 128 bits is so many possible values. Currently we're only using from 2000 to 3000. So this number, by the way, this number 2001, which we use in the labs, that's kind of like the 192.0 reserved for training and documentation type thing. That's a number that's not allowed to use on the real global public internet, real world internet. We use it for training and documentation and Cisco lab stuff. So in the Cisco labs, you're always going to see IP version 6 address is always going to be something like 2001 DB8 ACAD Network Academy. Oh, that's so clever. So the global routing prefix, when you have a company and you get a bunch of /64 addresses, well, that's billions and billions of possible addresses. As a matter of fact, if you hook up the cable company and they support IP version 6, you're going to get 6 billion addresses. Doesn't matter that you only need 10 or 12. So they're just throwing these things out like, candy, wasting them. If you are a service provider, you would give a /48 to a company because they might have hundreds of branch offices and they all need a 64. So we're going to subnet our 48 into 65,000 /64s. Within a particular company, everybody in the Fort Worth home office will use one /64. So let's look at this configuration that we would do on a router. Typically, we would say interface G00, and then we'd say IP address 192.168.1.1 and do the no shutdown command. When we type in our IP version 6 addresses, and almost all the commands that are on the routers and switches that are like IP address, we change it to IPv6 address to tell it it's going to be the 128-bit address instead of the old 32-bit IP address. So we can type IPv6 address, and there he has the 2001 DB8 ACAD, and he's used a colon here to represent a bunch of zeros, so he doesn't have to type so many zeros. Feel free to type out all the zeros if you want to. If you want to type all the leading zeros and all the strings of zeros together, you can do it, but you're allowed to save typing and omit the leading zeros and omit the large strings of zeros once to save typing and save space. The control panel on a Windows machine is very similar to the IP version 4 control panel. We can obtain an address automatically, or we're going to statically configure them. So in this case, he's typed in an address of, if this is an IP version 4 machine, it would probably be 192.168.1.10. And his default gateway would be 192.168.1.1. So instead, we have our 2001 DB8 ACAD 10, and his default gateway is 1. So we usually make them try to correlate to each other. And we're us network technicians and engineers are used to .1 being the router and .2 being the switch. So we can configure them manually. In a home or a business environment, we won't use static addressing, but we'll have a dynamic thing. We have DHCP. There's a version of DHCP for IP version 6. And then this zero config movement, automatic address configuration and movement that arose when IP version 6 was put together. The technicians or the engineers and designers said, try to make everything automatically configure itself. So there's something called stateless address auto configuration, Slack. Cut me some slack, which can automatically assign an address to a workstation. So cut me some slack works like this. The workstation, when he boots up, is going to send out a message saying, I need to get my IP address and my prefix length and the default gateway address. This is kind of stuff that in an IP version 4 world you would get from a DHCP server, or you have to statically configure it. So the local router sends out router advertisement messages telling everybody who he is. And the workstation sent out a router solicitation message saying, I need to get my address. There's 3 ways to do this. We can automatically configure it and get it from the router. We can get some information from the router and some from a real DHCP server hardware, which costs money and you have to configure it and install it. Or we can go completely to the DHCP version 6 server and get everything from it like we do now with IP version 4 with a DHCP server. So there's 3 possible options here. So the default is Slack only. Get everything from the router. The workstation will come up with his own address by manipulating his MAC address or just making up a number randomly. And it'll get a 64-bit prefix from the router. Option 2 is get some from the router and some from the DHCP server. And option 3 is get everything from the DHCP server. Now let's look at this process of coming up with the host address, what we call the interface ID with the IP version 6. So if it's Slack, the router will tell me the prefix. He'll tell me the network he's on with the first 64 bits. I need to get my own 64-bit network address. So there's 2 ways I can do this. I can take my MAC address. So what's just shown, and we're going to do rocket surgery with our MAC address. We're going to take our MAC address and we're going to split it into 2 pieces. It's going to split it into 2 chunks. Then he's going to insert this FFFE value in the middle and flip some bits and come up with a unique 64-bit interface ID value. And that's going to be the end of his address, and the first 64 bits of his address, the first half will be what the router told him. Some devices use this, and some devices use a different method where they just randomly generate it. Depends on, like for example, Windows 7 and Windows 10 use different methods depending on what it is. The random method is here in green. I got this from my router. He told me what my network was. Good. Now I can send stuff to my default gateway value and send it to the other networks. And I just made up, out of nothing, I just made up a random value. Now, what are the chances if I take a 64-bit value and make up a random number that it happens to be the same as what another workstation made up? It's almost impossible for that to occur. But just in case, I think the chances are greater that you would be hit by a meteorite, tomorrow. But just in case, there's a special protocol called DAD, duplicate address detection,
The workstation will make up a random number, and just make sure that no one else is using it. He'll ask if anyone else happens to have used this particular number, and if so, he'll make up a new number. So link local addresses can be established dynamically, which we're normally going to do in the real world, or you can configure them manually if you want to, which we'll do in the Cisco labs. So Cisco routers use the EUI. English, someone's joining. Oh, he timed out. English, my web advisory timed out on me on my attendance screen. I got to do it again. Come on, log me back in here. Go to semester, go to CCNA, go to attendance tracking, go to the last. Add the student. So we got 1, 2, 3, 4, 5. Okay, good. Did he do the update? Great, he did the update. All right. So Cisco routers use this EUI. They chop up the MAC address and they come up with the bit swapping number. And that guarantees uniqueness because the manufacturers are forced to use unique 48-bit MAC addresses for every interface, Ethernet interface they create. So it's a kind of cumbersome to type in. It's a bunch of numbers you have to type in, usually not a bunch of zeros. So if I do static addresses, I can come up with an easy to remember number like, for example, the link local address, FE80::1. That's very easy to type in. That's why it's commonly used for router ports. Easy number to remember. And since it's locally significant only, I can use the same value on all the ports of my router. Just like you can use 192.168.1.1 on your home router, I can use 192.168.1.1 on my home router. On the Cisco devices themselves, everything that was, for example, we had show IP interface brief, for short. Most commands, almost all that show IP something, if you want to show the IP version 6 something, you simply type show IPv6 instead of show IP. So I typed show IPv6 interface brief if I wanted to see the IP version 6 addresses I've configured. I would type, instead of show IP route, I would show IPv6 route. Ping command is just the same. So I can type the ping command. Instead of typing the dotted decimal IP version 4 address, I'll type the IP version 6 address and see if I can ping it properly. It'll work just the same as what you're used to. Multicast addresses are used for this process of the router sending out his network prefix and the workstation sending back the request to the router. It says, give me a prefix and tell me, should I go to the DHCP server or not? Solicited node multicast address. Oh man, this sounds really complicated. So this is a special Ethernet multicast address to find destination MAC address. So a workstation would, for example, would probably not be interested in routing table updates between routers and different routers. He would ignore this. He would filter it. Now let's look at connectivity verification. In IP version 4, we got something called Internet Control Message Protocol, ICMP, which is a bunch of different messages of which we're going to use echo request, echo reply. That's how ping works. When you type the ping command, you send out an echo request, and the workstation replies with the echo reply, and you get the message back in ping that you have connectivity with him. There are other messages in ICMP that routers use between each other to determine if networks are available or not. In IP version 6, he has ICMP version 6 router solicitation and router advertisement messages. Now remember I told you when Mark rant mode that they decided instead of calling it broadcast, we want to feel good about it, we're going to call them Unicast, so that the marketing boys can claim, oh, there's no more broadcast in our messages. Well, yeah, they still are there. They're just not calling them broadcasts anymore. They're calling them Unicasts. We still need a way to discover our neighbors. Instead of sending out ARP broadcast and getting an ARP reply, we're sending out router solicitations and router advertisements and neighbor solicitations and neighbor advertisements. And the duplicate address detection that I mentioned before, if I make up a 64-bit value out of whole cloth, I need to check with dad and make sure that I didn't happen to make up the same number that my neighbor made up.
So it's the same exact function. It's still sent to everybody else in the world. Switches still flood them to all the other ports, but we feel good about it now because we don't have to call it broadcast anymore. So I want to test my local stack in IP version 4. I type ping 127.0.0.1. And when I type that value, that proves, if I get a ping back from it, that proves that I've checked the IP version 4 checkbox in the network control panel. In IP version 6, they didn't waste a whole class A network. They made it : 1. They just the first one out of the 600 million trillion quadrillions values we got in IP version 6. So we don't have to waste those values, even though we got so many, we can throw them away. Next step is I want to ping, I'll ping my default gateway. So I'll ping 10.0.0.254, and echo request will be sent to the router if we have connectivity, in this case through the switch, and he'll send back an echo reply. And on my screen, I'll see reply, 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 reply. I have successfully communicated with that. Now, typically the first 1 or 2 of pings will fail because in the background, ARP has got to line up or correlate your data link layer 2 address with your layer 3 network layer address. That sending out that broadcasting in the reply will kill the first 1 or 2 pings. But that's held in memory. The ARP cache holds that in memory for about 3 minutes. If you subsequently ping again, you'll get all successful on that. It's just enough to make you nervous when you do the first ping and you think you have an error, and then it starts working. Next step, I want to ping a remote workstation. I want to ping another workstation on another network. So I'm 10.0.0.1, and I'm going to ping another workstation from another network, 10.0.1.1. And the router connecting the 2 networks together. He'll have a routing table that's converged and is proper. He can find both workstations and send messages back and forth to them. So ping is a useful tool for proving that the network is operating properly. Now, ping tells us whether the connectivity it either works as a whole or it fails. And if it fails, I have no idea where the problem has occurred. So traceroute is something I call ping on steroids. Traceroute is kind of like it will ping each individual hop. In this graphic, we have 3 routers. And he'll ping each router individually. Essentially, he pings each router individually and then types out on the screen that he's connected to each one. And you can see if the connectivity is lost. For example, let's say this phone line went down. This ping would work, and this ping would work, and this one would fail. And I would know the problem lies somewhere between these 2 routers, and I could try to fix that or call the service organization I subscribe to and have them try to fix it. So ping works by testing each individual link and making sure that it works properly. Okay, let's stop this one. And it's time for the dreaded, feared, and hated subnetting. Okay, so let's say I need to be able to share an application, and I need to be able to share this PowerPoint slideshow. Okay, there we go. Okay, do you remember what I just talked about? Oh, yes. The definition of a network address is all the host bits are set to 0. The network prefix can be any arbitrary prefix, but if the host bits are all 0, typically on a /24 network, that'd be the last 8 bits. If it's a broadcast address, all the host bits are set to 1. So that'd be used for a broadcast function like ARP or DHCP. Any other value that's not all 0s or all 1s is a valid address to give to a real host machine, like a desktop PC or a server or a printer. And remember this, for a host to communicate directly with another host on the same network, they must have the same network prefix or network portion. So with every network range, IP address range, that we divvy up to networks, we automatically lose 2 addresses. The network address, sometimes called the subnetwork address or wire address, definition, all the host bits are 0. That's the network identity. And we lose the last one, which is when the host bits are all 1. That's the broadcast address for that network. We get all the others that are left over. So in a /24, we have 8 host bits, to the power 8 is 256. We lose 2, 256 minus 2, we get 254 addresses we can use. Depends on the different networks of different sizes you can have, but you always lose 2. So our general formula is however many number of bits we have in the host portion, we lose 2 of those. If we have 8 bits, 2 to the power of 8 is 256 minus 2, we have 254 addresses. If it's a huge network like a Class A network, well, there's 24 host bits in a Class A network because it's designed for really large networks. I have 16,777,216 possible numbers. The one with the 24 zeros I lose, the one with the 24 ones I lose for the network identity and the broadcast function. So I only have 16,777,214 addresses left over. For a Class B network, there's 16 host bits. So 2 to the power of 16 is 65,536. I only get 65,534 addresses that I can use. So ever since about 1995, we've gone away. Let's see, there was a guy on the radio that was an expert on music trivia, rock and roll music trivia, and he used to say, rock and roll ended in 1975. He knew everything about music before 1975. Classic rock and roll. Classful addressing ended in 1995 because we were running out of addresses and we need to reprogram all the routers in the world to keep operating. So we're going to use classless addressing. Now, instead of giving you a Class C address, which has 250 addresses, or a Class B address, which has 65,000 addresses, or a Class A address, which has 16 million addresses, we're going to give you one that's more suitable to what you need, using something called variable length subnet masking. I'm not stuck with the /8 or the /16 or the /24. I can do any number that I want to get something that wastes the fewest amount of addresses. Okay, so let's look with an IP. Let's look at what we do with an IPv4 network. We're going to find the network address for the host, find the broadcast address for that host machine, what host addresses are available, and then we'll look at dividing a large network into smaller networks. Okay, thank you, Homer. So here we have a router connecting 4 networks together, and they've been assigned different unique network addresses. Every host machine on each individual network, there are 4 individual unique networks in this diagram, they can connect with other devices directly because they have the same network prefix numbers. Have that same network number, same subnet mask. So routers use this network number to build their routing tables. That's why we can't use it for a host machine. The router needs it. What's the definition of a network number again? All the host bits are 0. So when you look on the routing table, show IP route on a router, you'll see that that's all the host bits are set to 0. If a host needs to send out a broadcast address, he uses the network number and he uses that special reserved value, all the host bits are set to 1. Like on our common network, 192.168.1, the broadcast address will be 192.168.1.255, which is a binary of all ones. So I can't assign that to a host. It's reserved for the broadcast function only. The host number is the portion of the IP address that uniquely identifies the individual host on the network. I can't use all zeros, can't use ones, but I can use 0000001, 2, 3, and 4. On a /24, I have 250 more addresses I can use. Those are valid addresses that I can assign. Okay, the subnet mask. Each class has a sort of a default subnet mask. With a Class A network, there's 8 network bits. So there's not that many Class A networks. There's only 250 of them or so. But each one of these networks is very, very large. It has. So the default subnet mask, the /8, means 255.0.0.0. Our Class C network that we use in our labs, there's 24 network bits in the prefix. Everybody on the same network will be, so for example, maybe 192.168.1 would be the network prefix. And then we would use the last octet of the IP address to assign to our host machines. Remembering again, we must reserve the 0 value for the network identity and the 255 value, the all ones, for the broadcast function. So in a Class C network, the address range, the prefix is 192 to 223 because of the way they set up the binary numbers to allocate these out. 24 network bits. These are the values shown in orange and on our screen. 24 network bits. Okay, 2 to the power 24 is a pretty big number. You can have over 2 million Class C networks. There's 8 host bits, that's the white bits in the host value in the last right-hand side of the diagram. So I have 8 bits, 2 to the power 8 is 256, minus 2, because I have to lose all zeros and all ones for the network value. And that gives us our default subnet mask of 255.255.255.0 or /24. Turn this back on and bring this back up. Where did it go? There we go. So for my Class C subnet mask, the first 24 bits is the network prefix, the network number, and the last 8 bits of the host numbers. The first host address is reserved for the network address. In this case, we have 210.20.17 as an arbitrary prefix he came up with. The last host address, all ones, is reserved for the broadcast address. These are the ones we can assign to host machines. They're reserved for the network function of network identity and broadcasting. The host addresses that are remaining can be used. We can take the 0000001 in yellow. That's our number 1.1. All the way up to 1111110.254. Can't use all zeros, can't use all ones. Those are reserved. So that we still have 254 addresses we can use. In a Class B network, there are 16 network bits and 16 host bits. The range of the first number in the dotted decimal address is 128 to 191. So there's 16,000 of these addresses. There are 16 host bits. 2 to the power 16 is 65,000. The number of usable hosts per network is that 65,536 minus 2. And the default subnet mask for a Class B network is 255.255.0.0. So in a Class B network, the subnet mask is this /16. The first 16 bits of the network prefix, last bits of the host numbers. So the first host bits are all zeros. The 16 yellow zeros, that's our network identity. Cannot use that for printers, servers, employee desktop PCs. Only the routers can use that for their routing tables. When the host bits are all ones, that's reserved for the broadcast function. Gonna go. Okay, good. The host portion is all zeros. The remaining host bits that we can use. So 2 to the power 16, 65,536 minus 2, we get 65,534 host machines we could use on this network. So that's quite a few numbers that we can use. A Class B network we call it medium size. It's much larger than a Class C network would be. Class A networks, the address range is 0 to 127. So there's 8 network bits, 24 host bits. This is a gigantic network because 2 to the power 24 is over 16 million. We lose 2 of those values for all this. The 24 zeros is the network number, the 24 ones is the broadcast function. We don't get to use those. However, network 0 is reserved for the wildcard function for our routing. Static routing thing we'll do later in a later course. 127, the whole 127 is reserved for the 127.001 loopback test, just to make sure that's working properly. So we know the first 8 bits is the network prefix. The last 24 bits in yellow are the host numbers. This is the reserved network identity. We cannot use this value. The router only can use this value for its routing table. When the last 24 bits are all ones, that's reserved for the broadcast functions like ARP or DHCP. But we get all the ones in the middle. We get over 16 million addresses we could use on that network. And we're a huge corporation like IBM or Microsoft. We need all these numbers. So let's look at this /16. What address class is this? Well, /16, that's a Class B. What's the subnet mask, the default subnet mask? Well, the number of binary bits in 255.255 is 8 plus 8 is 16. So 255.255.00 is the default subnet mask. What is the network portion of this particular address? It's the first 2 octets with the last 2 octets set to 0. So it's 130.61.0.0. What's the broadcast address? What's our definition of a broadcast address? All the host bits are set to ones. So 130.61.255.255, which is all ones in binary. What are our usable host addresses that we can use? Well, the 65,534 minus 2. So 0.1 to 255.254 are the over 65,000 addresses we could use in this particular network. Okay, a /24. That's a class C address. Subnet mask, 255.255.255.0. The network prefix is the first 3 octets, with the last octet set to 0. Remember, 0 is a reserved value for the network. To identify this as the network identity of this network. Broadcast address, let's change that 0 to a 255. That's a broadcast address for a Class C network. So we get 254 available addresses from .1 to .254. Perfect for small businesses or residential applications. Okay, Class A address, pretty big here, 64 dot. That sounds like AT&T. I think they got 64 dot. They're a pretty big company. So what class address is this? It's a Class A address, the biggest class. The normal default subnet mask is 255.0.0.0. The network prefix is the 64 dot. Definition of a network address. All the host bits are set to 0, so all 24, the last 3 octets are all set to 0. Broadcast address is 64.255.255.255. The number of usable host addresses is a whole bunch, 2 to the power 24 minus the 2, minus the all zeros and minus the all ones. So they go all the way from 64.0.0.1 through 64.255.255.254. Okay, let's do a little subnetting. We're running out of IP version 4 addresses. And typically a company gets a bank of addresses that they are used. It would be wasteful for a company that got a Class B address and they, just because a Class C address wouldn't work for them because they have 256 hosts and a Class C address would only give a 254. So they give them a whole Class B address. They used to give these addresses like candy for free. So I'll give you an example. When I worked for Harcourt in the 90s, we had 65,000 addresses and we only used about 12,000 of them. We were wasting 3/4 of these addresses. So we had applied to the name and number authority people, INAA, and they gave us these numbers. However, we did have branch offices throughout the world. We were on every continent except Antarctica. We had about 200 branch offices throughout the world. And we needed to take this Class B address and subnet it into different address values for different departments, different offices in different cities. So what we're going to do is, we couldn't plug them all together into one network because all the broadcasts would eat us up. There's a definite limit to how many broadcasts you want on a single individual network. Now, they make some pretty big switches these days that you can plug 200, 300, 400, 500 people into the same switch. Anything over about 500 on one network, the broadcasts are going to consume too much traffic. We need to chop it up into smaller networks. And when we do this, we'll give each network its own network prefix, its own network value. So if a company has multiple networks connected by a router, we're going to use the unique network numbers for each one. So maybe this company was given the prefix of 131.15.0.0, sort of a legacy Class B address, and he's going to use them for all of his networks. I like to compare this to when you get a phone number bank. TCC we're 817-515. All the Tarrant County College phone numbers are 817-515 something. So South Campus is 515-5000. And Northeast Campus is 515-4000. They can split them up and divide those numbers. The telephone administrator can divide those up among all the networks. So network administrators and technicians will divide up a network prefix among all the different networks. So let's take this 131.15 network and divide it up. And this is totally arbitrary. We're going to just make sure we use unique numbers. And we have the 1 dot network and the 2 dot network and the 3 dot network and the 4 dot network and the 5 dot network in red. That's a least telephone link that connects the networks together. So telephone numbers, network numbers must be unique. The telephone numbers must be unique too. So plan for your needs now and for the future, and try to use the network's numbers efficiently, and plan for future growth and an expansion that may occur in the future when you add stuff up. Now let's subnet our networks. And this is what I call the binary robbing of Peter to pay Paul. So let's say I was assigned that I was at Harcourt and I got 167.208 as my network prefix. And I want to divide that up because we have 200 branch offices throughout the world, and we need to assign a different unique network prefix to each different one. So what we're going to do is we're going to borrow bits. We only have 16 bits in our original network prefix. We're not allowed to change that because someone else has got the other values of the other 16 bits. We can't steal theirs. But we can take our host bits and we can borrow bits from the host portion and give them back to the network portion and create new smaller networks. So we have new multiple networks, and they're slightly smaller. So it's a subnet of the original network. These borrowed bits become a new network number with a bigger prefix. So for example, I could take my /16 and make 256/24s. And then each of the individual offices will look like a /24, which is the most common network prefix you see anywhere. Even no matter how big the company is, it's almost always a /24, maybe a /23. So the subnet mask will change. The original subnet mask was 255.255.00. We borrowed 8 bits, those 8 ones shown in yellow, and gave them back to the network prefix. So our new subnet mask is now 255.255.255.0. We have to borrow them from left to right in descending order. We have to leave at least 2 bits for host addresses. And we can't give all zeros or all ones to a host address. It has to be a unique value. So how many subnets do I get? Well, in this case, I borrowed 8 bits. How many new subnets do I get from my original master network that was really big but had to be divided up among my 5 continents worth of offices? Well, I borrowed 8 bits to the power 8. I created 256 new subnets. And how many usable hosts are there on each of those new subnets? Well, I have 8 host bits now. So 2 to the power 8 is 256 minus 2 because I lose the all zeros and the all ones. So that's where you can come up with the value of how many host bits you get. We have to leave at least 2. We can't borrow, we have to leave at least 2 bits left over, so you can't borrow more than the 6 bits in a Class C type network. Okay, so let's have our Class C network, and we decided we need to divide it up. Looks like we got 1, 2, 3, 4 networks in this topology diagram. We need 4 networks, and there are 5 hosts in each one, and we want to leave some room for future growth and expansion. Now, looking at the chart at the bottom, I could borrow just 2 bits, and that would work right now, but it wouldn't give me any room for future growth and expansion, and it would be too many. It would be lots of host addresses I'm wasting on each individual one. What if I borrow 3 bits? Well, I create 8 new networks, and there's 30 hosts available, 30 hosts that are available on each one. There's only 5 hosts on each one. That would be a more reasonable value to do it. So let's borrow the 3 bits. We're going to borrow 3 bits. 2 to the power 3 is 8 subnets, and there's 5 bits left over in the host portion. 2 to the power 5 is 32, minus 2 for the all zeros and all ones. We have 30 hosts. Well, we only have 5. Now we can add new offices. We can add new employees at each office and have some room for future growth and expansion. So try to look to the future. Okay, it's time for the magic number. The magic number is a number that tells us when we create our subnet charts, we're not going to have to convert back and forth between binary and decimal. Let's just stay in the decimal domain. We're used to the decimal number system since 2nd, 3rd grade. So in this case, we had 5 host bits. 2 to the power 5 is 32. 32 is our magic number. Let's see how this works. Remember our original network? It was 192.168.80.0 that we got from our ISP. And we determined that we needed to borrow 5 bits. So our new subnet mask is the /27, 255.255.255.224. Okay, it's time for 3rd grade multiplication. Here's our original network address. And here's I joke in this class, if you ask a computer science professor to count on his fingers, he won't say 1, 2, 3, 4, 5. He'll say, oh, 0, 1, 2, 3, 4. So we always start with number 0. Okay, so the first network is network 0. And look at that last octet. What's the network address? What's our magic number? 32. What's 32 times 0? It's 0. So what's the first number that we can use? Oh, we're going to put the last broadcast address for the whole thing at the end. So if my reserved network address is 0, what's the first value I can use? Well, first of all, let's figure our network addresses. What's 32 times 1 is 32. 32 times 2 is 64. 32 times 3 is 96. 32 times 4 is 128. 32 times 5 is 160. Times 6 is 192. And times 7 is 224. Okay, all third grade math so far. Now we have our network prefixes that we're going to use. Now we only needed 4, but we have 4 more for future growth and expansion. Okay, the broadcast address is always the next network address minus 1. So network 1, you notice his network address is .32. Subtract 1 from that. .31 is the broadcast address for that network. So let's construct our broadcast addresses for each one of these banks of 32 addresses. In between those, 0 on the left and 31 on the right is the range of addresses we get to use. Well, 0 plus 1 is 1. 31 minus 1 is 30. Here's our 30 available addresses. Remember 2 to the power 5 minus 2? 2 to the power 5 is 32, minus 2 is 30. We have 30 usable addresses in each new network we've created. And we've subnetted and have to use any binary. Isn't that cool? Now we take these addresses that we made and just arbitrarily assign them out to our 4 networks, 0, 32, 64, 96, and we have a bunch of addresses we can use in the future. We don't have to change our original scheme. You don't want to do that. That's too confusing and too difficult to do. You always want to think about the future. For Class A and Class B, it's more bits. You simply determine how many networks do you need to create, how many hosts on each network, and then determine the number of bits to be borrowed, find your magic number, and then subnet. So let's say you have a Class B network, and you have 7,500 users. There are 10 worldwide central offices. Some of the offices have 3,000 machines. Some of the offices only have 100 machines. So we got a Class B network from the network authority people, or we got it from ISP. Each central office will handle their own network, and you just further subnet them for your particular one. So let's use 172.25 as our network prefix, /16. And we need to divide it up among our 10 offices. Now, each individual office, Central 1 will do its own subnetting, Central 2 will do its own subnetting. You just have to come up with the prefixes. So let's see now, if I just borrowed 1 bit, that would only be 2. Well, wait a minute, I need 10. If I borrowed 2 bits, that would only give me 4. If I borrowed 3 bits, that would only give me 8. But if I borrowed 4 bits, well, 2 to the power 4, 16 networks. Well, that's good. I have 10 networks that physically exist. And there's a little room there for future growth and expansion. How many host bits does that give me? Oh, well, that gives me 12 host bits. 2 to the power 12 is 4,096, so I get 4,094. My home office had 3,000 people. That's good. It's big enough. So it looks like borrowing 4 bits is the best bet for this particular scenario. Now, what's our magic number? So our magic number is going to be 2 to the power 4 or 16. So 16 times 0 is 0. 16 times 1, look at the third octet of the IP address. 16 times 2 is 32. 16 times 3 is 48, and so forth. Our broadcast addresses are always the number in the next column minus 1. So 64.0 minus 1 is 63.255. And then we simply fill in the ranges of addresses we have available at each branch office, the 4,000 or so addresses we have at each branch office. Okay, is that it? That's it. Okay, good deal. All right, now hang on just 1 second. No, don't save. No, don't save. Oh, let's see. Can I stop sharing this? So I want to share. Okay, So Wednesday, the people that come in person will do this lab 6.4.3.5. No IP version 6, thankfully. It'll be IP version 4 exercise where you'll hook up a switch and a router and a PC. And this will be the first, last time you used the router and you sort of did some show commands. This time we'll really configure the router and do some stuff on it. So, and I will tape that presentation with the real routers at the school. And I'll also do a packet tracer demonstration for you guys that are going to do it on packet tracer by yourselves. Okay, good deal. That's another one for the books. Hang loose. I'm going to stop recording.